In this lesson, we're going to talk about a very important theorem called the mean value theorem. But before we actually get to that theorem, we have to figure out where that came from. So we're going to look at Rolle's theorem. So Rolle's theorem says to let f be a function that satisfies the following three hypotheses. So f is continuous on the closed interval a to b, f is differentiable on the open interval a to b, and f of a is equal to f of b. So if all three of these conditions are met, then there is a number c within the open interval a to b such that f prime of c is equal to 0. So basically what this means, here's four examples of Rolle's theorem. This means that we have the same endpoint. So a and b are going to be at the same y value. So a and b obviously are different x values, but they have the same y value. It's differentiable on the open interval, meaning that a derivative exists at every point within the interval. Then there must be some point c, or in some cases multiple c's, where the derivative is equal to 0. Right, so we have a slope of 0. So we can see when we have a straight line, you're always going to have a slope of 0. So there's different points within this interval. And the second, we have a maximum point here, which has a derivative of 0. Here we have two different derivatives of 0 at c1 and c2, and then here we have another derivative of 0. So all of them have the same y value for their endpoints. They're all continuous. They all have derivatives within the interval. So all three things are met, and therefore there must be some place within a to b that has a derivative of 0. Okay, so let's look at an example. So verify that f of x equals x squared minus 2x cubed minus 2x squared minus 4x plus 2 satisfies the three hypotheses of Rolle's theorem on the interval -2 to 2. Find all numbers c that satisfy the conclusion of Rolle's theorem. Okay, so this is the function that we're dealing with here. So we have to check our three hypotheses. So the first hypothesis is we have to see, is it continuous? Well, this type of function is a polynomial. All polynomials are continuous. So on the interval from -2 to 2, this is continuous. So we can say that f of x is continuous on -2 to 2. And I'm going to put because it's a polynomial. Okay, so if it was, let's say, a rational function, and there were places where it is not continuous, right? There's points of discontinuity, then it would not meet this criteria, and it would not satisfy Rolle's theorem. So now let's look at number 2. So the second hypothesis said that it has to be differentiable, meaning it has a derivative everywhere on the open interval. So if I take the derivative of this, right, f prime of x, this is going to give me 3x squared minus 4x minus 4. So again, I have a polynomial. So since I have a polynomial, I know that I'm going to have a derivative at every point within my open interval -2 to 2. Polynomials are differentiable. So this is going to be differentiable everywhere. On -2 to 2. So that is also holding true. So now for the last hypothesis we have to check, we have to see if f of a and f of b are the same. So if the y values of my endpoints are equal. So first, we could see from our interval, right, -2 to 2, we know that a is equal to -2 and b is equal to 2. Right, these are my two endpoints. So what I'm going to do is figure out f of a. So that's going to be f of -2. So I'm going to plug -2 into my original function, and that's going to give me -6. So now I'm going to find f of b, which is f of +2. I'm going to plug +2 into my original function, and this is also going to give me -6. So this is proving that f of a is equal to f of b, because -6 is equal to -6. So check. So all three of these are true. So since all three of them are true, we know that it satisfies Rolle's theorem. So now we have to find all the numbers C that satisfy the conclusion. So we have to take, we already found the derivative. All right, so I'm just going to rewrite this. So f prime of x is 3x squared minus 4x minus 4. So what Rolle's theorem is saying is that at some point C, the derivative has to equal 0. So I can factor this. And this is going to give me x minus 2 and 3x plus 2. And I'm going to set it equal to 0. So x is equal to 2, and x is equal to negative 2/3. Okay, so going back real quick to here, this is my conclusion. So there must be a number C in the open interval a to b such that f prime of C is equal to 0. We found that the derivative is equal to 0 when x is 2 and x is negative 2/3. But remember, it needs to be on the open interval. So my interval is negative 2 to 2 and it's closed. So since 2 is one of my endpoints, I cannot include 2 in my answer. Since it's not open, it's closed. So we would say that on the open interval, negative 2 to 2, only x equals negative 2/3 satisfies the conclusion of Rolle's theorem. Okay, so just as a recap of that, we had to first make sure that Rolle's theorem held true here. So we had to check our three hypotheses. All three were correct. Since all three were satisfied, we just had to set the derivative equal to 0 and find the values that make that happen. Once we found our values, we had to just check it against the interval. Okay, and we excluded 2 because it's an open interval we're talking about, so we cannot include one of the endpoints. Okay, so typically Rolle's theorem is not tested on the AP exam as far as Rolle's theorem. Like, you still need to know what Rolle's theorem is. They might ask a multiple choice question about Rolle's theorem, but typically the reason we learn Rolle's theorem is because that goes into the important theorem that we need for calculus, which is the mean value theorem. So the mean value theorem takes some points from Rolle's theorem and kind of changes things a little bit. So they're saying let f be the function that satisfies the following hypotheses. So here there's only two hypotheses. F is continuous on the closed interval, and f is differentiable on the open interval. So it's the same two as Rolle's theorem. Now Rolle's theorem has the endpoints being equal. F of A equals F of B. Okay, here it doesn't matter. We don't need to have the endpoints being the same. However, what this main conclusion is if these two things are true, then there is a number C in the open interval such that this equation, right? So what this equation actually is saying, these two are the same equations, 1 and 2. What the first equation is saying, f prime of C, remember f prime, that is the slope of the tangent line. So f prime is your slope of the tangent line. This f of b minus f of a over b minus a, right? That's how we would find the slope between 2 points. So this is the slope of the secant line, and that's between x equals a and x equals b. So what the conclusion of the mean value theorem says is that if the function is continuous on the closed interval and differentiable, meaning it has a derivative everywhere on the open interval, then there must be some number C where at that point C, the slope of the tangent line will equal the slope of the secant line between the endpoints. So equation 2 is just another way to rewrite equation 1. Okay, so we're mainly going to focus on equation 1 here. So to illustrate what I'm talking about here, if we look at this, the blue line is the secant line between A and B. The red line is the tangent line at point C. So there's some C value here where the slope is going to be the same as the slope of the secant line. So notice that these two slopes are the same, right? These lines are parallel. And you can see that the a and the b, the endpoints, they're not at the same y value. Okay? It doesn't matter if they're the same or not. What matters is that the slope of the secant line is going to equal the slope of the tangent line. Okay, here's another example. Again, the blue line is the slope of the secant line. So here we have two different values of c. We have 2 points where the slope of the tangent line will equal the slope of the secant line. Okay, so let's look at this example. So verify that f of x equals x cubed minus x satisfies the hypotheses of the mean value theorem on the interval from 0 to 2. Find all numbers c that satisfy the conclusion of the mean value theorem. So first thing we have to do is we have to check our hypotheses. So the first one is, I'll go back to here so we can see it. The first one is f is continuous on the closed interval. So the interval from 0 to 2. When I look at f of x, it is again a polynomial, so I know that it's going to be continuous, so I'm just going to write that out. So f of x is continuous on 0 to 2, and I'm just going to put because it's a polynomial. Okay, second hypothesis is, we'll go back to here, f is differentiable on the open interval from a to b. So again, differentiable means that it's going to have a derivative. So if I take the derivative, this is going to give me 3x squared minus 1, which again is a polynomial. So since I have a polynomial, I know that it will have a derivative everywhere between 0 and 2. So I will just write that here and say that it is differentiable everywhere on 0 to 2. So since both of these are true, okay, I'm verifying that it does satisfy the hypotheses of the mean value theorem. So now I'm going to use the conclusion. So f prime of c is equal to f of b minus f of a over b minus a. So the slope of the tangent line is equal to the slope of the secant line. So what I'm going to do is I'm going to find out f of b and f of a. So f of b is going to be our right endpoint. So I'm really doing f of 2. If I plug 2 into the equation, I'm going to get 6. I'm then going to find f of a. So a is going to be 0. So I'm finding f of 0. I'll plug 0 into the original equation. So I get 0. So what I'm really going to do here is just kind of plug this stuff in. So I already found f prime of x, right? That's 3x squared minus 1. So x and c are interchangeable. We had x as our variable, and they're calling it some number c. So you can use x or you can replace x with c. So I'm just going to replace it so it makes sense in this conclusion. So 3c squared minus 1, right? That's the derivative evaluated at c. So I took the derivative and I just plugged c in instead of x. F of b is 6. F of a is 0. And then b minus a, that's going to be 2 minus 0. So what I end up getting here is 3c squared minus 1 equals 6 over 2, which is 3. So now I'm solving for c. So I'm going to add 1. So I get 3c squared is equal to 4. I'm going to divide by 3. So I get that, I'll go up here, c squared is equal to 4 over 3. Okay, and then I'm taking the square root. So when I take the square root, I have plus or minus. I can actually take the square root of each one separately. So the square root of 4 is going to be 2. And then the square root of 3, I'm just going to keep it as square root of 3. Okay, we could rationalize this, but we don't really need to. So we get plus or minus. Now, we have to make sure that we check the interval, right? So it has to be within the interval or the open interval from 0 to 2. So negative 2 over square root of 3 won't fit in our interval, so we can't include the negative version. So the only value that's going to work here is going to be positive 2 over square root of 3. So that's within the interval, and that's the point where the slope of the tangent line is going to equal the slope of the secant line. Okay, so here's a graph of it. The black curve is our function, x cubed minus x. We can see that between a and b, so a is 0 and b is 2. Okay, so between 0 and 2, the blue line is our secant line. And then at point C here, that is where the tangent line is going to be equal to the secant line. And that C value that we found was 2 over the square root of 3, which is where that is. Okay, and the last thing we're going to look at is just what happens if we're not given an actual function. How can we figure some stuff out based off of our knowledge of the mean value theorem? So suppose that f of 0 is equal to negative 3 and f prime of x is less than or equal to 5 for all values of x. How large can f of 2 possibly be? So from here, what we're going to do is kind of interpret what we were given. So f prime of x has to be less than or equal to 5. So what that means is that f prime of c, right, the derivative, at most can be 5. Equals 5 is the largest, right? So it's saying that the derivative has to be less than or equal to 5. So the largest that it can be is 5. We have to figure out what interval we're using. So they told us that f of 0 is negative 3. So that is going to be my endpoint. For x is going to be 0. And then they ask us about f of 2. So 2 is going to be our right endpoint. So we're on the interval from 0 to 2. So let's use our mean value theorem. So f prime of c is equal to f of b, minus f of a over b minus a. So let's plug in things we know. So we have f prime of c is equal to, so we know a is 0 and we know b is 2. So I'm going to do f of 2 minus f of a, oh my gosh, not a, sorry, f of 0 over 2 minus 0. So from the original problem here, they told us that f of 0 is equal to negative 3. So I'm going to plug that in. So f of 2, I don't know what that is, minus f of 0, so minus a negative 3. So I'll just put minus negative 3. And then 2 minus 0 is 2. So I know that, let me go over here. So f prime of c is equal to f of 2. Because I have minus a negative, that's going to become plus 3 over 2. So what I'm trying to do here is I'm trying to solve for f prime of, well, I'm trying to solve for f of 2, right? But I have to figure out what f prime of c is. So what I'm going to do first is multiply both sides by 2 just to get rid of that denominator. So I have 2 f prime of c is equal to f of 2 plus 3. Okay, so then I'm going to subtract 3. So what I'm trying to solve for is f of 2 because it asked me how large can f of 2, possibly be. So f of 2 is going to equal 2 f prime of c minus 3. Now, they told us that f prime of x, or f prime of c, can be 5. That's the largest it can be. So since we're dealing with how large can f of 2 possibly be, we can plug in 5 for f prime of c. So we're going to have f of 2 is equal to 2 times f prime of c, which we're saying the largest option it can possibly be is 5, and then minus 3. So we're going to get f of 2 is equal to 10 minus 3, which is 7. So how large can f of 2 possibly be? The largest f of 2 can be is 7.